So here again, let's look at this question. And this is question number 24 in your worksheet. So the outer circular coil or the outer circular tube is again treated to be made up of these circular elements of infinitesimally small heights dy. And if you divide the whole of this length into capital N parts, then n into dy gives you L, right? So that is the value of uh, the length can be obtained from this equation. And the current per unit length for this wire, because the total current over the curved surface, right? The total current over the curved surface over here is I, and current per unit length is I by L. So we can simply find current flowing for this coil. Now, why do we need to find the current flowing for this coil? Because we are trying to find the magnetic flux associated with this small coil inside by calculating the magnetic field inside the circular tube. So to calculate the magnetic field inside our circular tube, our strategy will be to divide the circular tube into these small circular wires, and then the current through one wire is di, and this is number of turns per unit length for the complete solenoid. So we are treating the circular tube as a solenoid with these circular turns, right? So mu 0 small n into the current in one turn. The current in one turn is di, which is given here. So the magnetic field inside the tube will be found very easily, just substituting the value of di over here. This is the magnetic field inside the circular tube. Now the flux associated with this coil inside over here due to this field is simply found by multiplying this magnetic field with the area of this small circular coil inside and the wire loop, right? The area of the wire loop, and then the induced current can be found by taking derivative of phi, which gives you the EMF divided by the resistance of the wire loop. So that simply gives you this expression. And when you compare it with the given result, you simply get the value of very easily.